Hello everybody, I've got another physics video here today. Today I'm going to be going over units and notations, some algebra, exponents, kind of just a little bit of trigonometry too. Really just an intro to everything you need for Physics 1. So to start out, we're going to start with units and notations. So we're going to do a lot of unit conversions. When I like to do my unit conversions, I like to say what my unit is that I'm converting from and what I'm converting to kind of show what I need. So in this first problem, we're converting to meters per second for all of these actually. And we start with a sprinter running at 27.8 miles per hour. So I know I have miles per hour. I need to convert this to meters per second. So I can then say, okay, the first thing I need to do is convert hours to second, and then miles to meter. Or you could do miles to meters first, and then hours per second. It doesn't really matter which you choose. For hours, there are 3,600 seconds in an hour. So I'm going to multiply this 27.8. We have 1 hour on the top, and then 3,600 seconds on the bottom. And then there are exactly, for meters, there are 1,609.34 meters per mile. So what we're doing is we're dividing 27.8 by 3,600 and then multiplying it by 1,609.34. And when you do that calculation, you'll get 12.4 meters per second. For our next problem, we have 36 kilometers per hour, and we again want to convert into SI units. So we have kilometers per hour, and we want to put it into meters per second. So again, we need hours into seconds and kilometers into meters. For hours, again, we have 1 hour per 3,600 seconds. And then for kilometers into meters, there are 1,000 meters for every kilometer. So we divide 36 by 3,600, and then we multiply it by 1,000, and we get 10 meters per second. Okay, so for this next problem, we have 510 knots, and we want it to use the conversion factor that 1 knot equals 0.514 meters per second. So if we have a knot, and then we want to put it into meters per second, let's say we do, since we know that 1 knot equals 0.514 meters per second, that's the same as saying for every 0.514 meters per second, we have a knot. So we can have 0.514 meters per second on the top, and then 1 knot on the bottom. And then if we multiply by 510, you can see that the knots, this cancels with this and leaves us with just the meters per second. So we really just want to multiply 510 by 0.514, which is 262.14 meters per second. It can be a little confusing to know, like, okay, what do I put on the top and what do I put on the bottom? But it's always good to remember, like in this case that we just did, we wanted to get rid of the knots. We want it in meters per second. So you arrange it in a way that the knots are going to cancel each other out. Okay, so now we have a cheetah sprinting at 100 kilometers per hour. Go ahead and erase this other stuff. So we have 100 kilometers an hour. We want it in meters per second. So we can multiply it by 1 hour for every 3,600 seconds. That'll get rid of the hour. So we have kilometer per hour. We want meters per second. So first to get rid of the hour by dividing by seconds. And then and the reason that this works is because we have kilometer per hour, and then the hour is on the top over here. So these two are going to cancel out. And then after we have that, we have kilometers left over. So we want to divide by kilometers. And we know that there are 1,000 meters in a kilometer. So this becomes about 27.7 meters per second. Okay, so now we have some significant figures. So when you're presented with a problem, it's important to realize that the significant figures of anything, any problem that you're given, any number that you're given, is essentially everything that is not a zero. So in the case of this, we have 4 significant figures because we have 6,371 or 6,371,000, and everything, all of these are zeros, so they are not sig figs. We have 4 sig figs. Sometimes you might be asked to show something to a specific amount of sig figs. So like if they say show 2 significant figures, you'd only be interested in these 2. And then for scientific notation, I like to say that it's x point xx, and this is however many significant figures you have. So for us, we have 4 significant figures. So we have the point, and then times, I'm gonna use dot because that's too many x's, times 10 to the power of, we'll just say n being however far you need to move it. So in this case, we would need to move it 1, 2, 3, 4, 5, 6 to the left. So we have 6.371 times 10 to the 6th. It's a positive 6 because we're moving to the left. When we move to the right, it is a negative 6. So now for B, we have a 100-meter dash completed in 9.86 seconds. So this is actually already in the proper form, this 9.86. This is what we're interested in. Well, let's do the 100-meter and the 9.86. So for 100 meters, that is the same as saying 1.0 times 10 to the 2. So we'd move it to the left. For the 9.86, it's already in the proper form. It's, that x point xx, however many x's you have, and we have 9.86. So you don't need to do anything with that. So now we have the electron's mass. We've got a whole bunch of zeros and 911 kilograms. So I counted this ahead of time. You can double count if I'm wrong, but this is 24 spaces that we would move it to the right, giving us 9.11. So we move it this way to the right 24 times until the decimal ends up right here. And since we moved it 24 times, it's times 10 to the negative 24. That's in kilograms. Interesting fact, that's actually wrong. Whoever made this document was not right about that. They just put a whole bunch of zeros in there, which I don't blame them. The accurate electron mass is, I think it's around 9.11 times 10 to the negative 31 kilograms. And then for me, for why we prefer SI units over everyday English units, like miles per hour or pounds, this is a really simple answer for me, and that is it's because how everybody else does it. And so it allows for consistency all across the globe. It's also, if you get to higher and higher level physics, everything is in SI units. And so a lot of the equations will only actually work if you use SI units. If you try to not use SI units, like more everyday English units, you can encounter a lot of problems. So it's very important in physics to get good at your unit conversions. Okay, so now we just have a basic algebra review. I'm just going to go through these problems. So for A, we have 3x plus 5 equals 20. I would subtract 5 from both sides. So then you have 3x equals 15. 20 minus 5 is 15. And then you would divide both sides by 3. 15 divided by 3 is 5. So x equals 5. For this one, we have x squared minus 5x plus 6 equals 0. This is a quadratic equation. You can use the quadratic equation if you'd like, or you can use the shortcut to realize that we need something that adds to negative 5, two numbers that add to negative 5, and multiply to 6. So in this case, we have negative 3 and a negative 2. Negative 3 plus negative 2 is the same as negative 3 minus 2, which is negative 5. It's there. And then negative 3 times negative 2, the negatives cancel, and we get 6 there. So this then factors to show us that x minus 3 times x minus 2 equals 0. And so we have two answers for x here. We either have x equals 3 or x equals 2. And you could have also done the quadratic equation the same way. A reminder that the quadratic equation is, I gotta remember it now. Quadratic equation is negative b plus or minus the square root of it's b squared minus 4ac all over 2a. Okay, and the last little basic algebra problem we have 2 over x plus 4 equals 6. So I'm going to subtract 4 from both sides. Then we have 2 over x equals 2. So you can either, the way that I would do this is I would multiply both sides by x. So you would then get 2 equals 2x. And so you can see from that, you can either divide both sides or divide out the 2, or you can just see that x equals 1. Okay, so now we have a few exponential expressions. First one, we have x cubed times x squared. Whenever you have a to the n times a to the, or we'll say a to the x times a to the y, so the same coefficient, you can just add x and y together. So equals a x plus y. So in the case of this, we have x to the 3 times x to the 2. 3 plus 2 is 5. So this problem would be x to the 5. Next question, we have y squared and then all of that raised to the power of 3. Whenever you have some coefficient raised to the power of x, and then that raised to the power of another exponent, this becomes a to the x times y instead of adding them together. So in this case, we have y squared to the power of 3. So this would become y to the power of 2 times 3, which is y to the 6th. And then finally, we have y to the 1/2. And whenever you have anything to the 1 over something, so y to the 1 over x, this turns into that x root of y. So in the case of y to the 1/2, it turns into the square root of y. And for square root specifically, it's implied that it's a 2, so you don't actually need the 2 there. But say it was a 3, you would want the 3 there, or if it was a 4 or anything else, you would want it there. Okay, so now we have the equation of a line. There's a slope 2.0 passing through the point 0, 4, and it wants us to sketch it. first thing I'm going to do, so I'm going to find here, I'm going to say that this is 0, 4. This is my y-axis, this is my x-axis, so this is x equals 0 right here. This is y equals 4. So I know there's a point here. I know it's a slope of positive 2, so it's going to go that way in a straight line because it's just a concept or a constant. So it wants me to find the slope and y-intercept. Oh, sorry, this is a different problem. Now it wants me to find the slope and y-intercept of a line passing through -2, 1 and 3, 6. So I'm going to draw a line to show that this is a different problem. So the slope, I'll call the slope m, is determined by the change in y over the change in x. And the best way to do this is basically you just take the bigger y and subtract it by the smaller y, and then you do the same with the x. So in the case of -2, 1 and 3, 6, the bigger y is 6, the smaller y is 1. So we have 6 minus 1. And then the bigger x is 3, and the smaller x is -2. So we have 3 minus a -2. And it's important to also realize that you have to pick one and stick with it. So if we had, like, let's say that this one is +2, that'd be the same problem. Basically, if you pick this to be your bigger y, this one also has to be your bigger x. Okay, so this simplifies. We've got 5 over 5, and that, of course, is just 1, so we have a slope of 1. The intercept here is going to be whenever y is equal to, or sorry, whenever x is equal to 0. The way that I always find the y-intercept is you use your slope-intercept equation, which is y equals mx plus b, where y and x are coordinates and m is the slope that we've already found. So I'm going to change this to be y equals just x plus b. And that'll give us, this way we can find b, which is the y-intercept. So we can pick one of our points and plug it in, and that'll give us b. So I'm just going to pick this second point that we had here, 3, 6. So that gives us 6 equals 3 plus b. You can rearrange that if you'd like. This shows clearly that b is equal to 3. And that is the y-intercept. So that would show us that if we were to put x equals 0, then y equals 0 plus 3. So the y-intercept equals 3. Okay, so now we have a basic trigonometry refresher. We've got a right triangle with legs of 5 meters and 12 meters. It wants us to find the hypotenuse and both non-right angles. Anytime I'm dealing with trigonometry, I like to draw it out. So I'm going to draw it down here. We've got this here. Say that this is our 12 meters and this is our 5 meters. Yeah, 5 meters and 12 meters. So it wants us to find the hypotenuse. We'll call that C. And then we'll call this one theta 1. And this one theta 2. So in this case, we have to use the Pythagorean theorem, which is that c squared equals a squared plus b squared, with a and b being the two legs of the triangle. This can be simplified to say that c equals the square root of a squared plus b squared. So in our case, c is going to equal 5 squared, which is 25, plus 12 squared, which is 144. And then you can do the math on this on a calculator, but this simplifies to be 13 meters. So that is our C value here, 13. In the case of the angles, this is where we really have to use our theta values. I'm going to use tangent to find theta 1. We'll do theta 1 first. So it's important to remember that tangent of theta equals the opposite over the adjacent legs. So in the case of theta 1, we have the opposite leg being 5 and the adjacent leg being 12. You can then rearrange this to say the inverse tangent is 5 over 12. And this is going to equal theta 1. And if you plug this into your calculator, you'll see that it is 22.62. Since we have all three legs, you can use any of the identities that you'd like. So you could also use, I'll write them over here, that sine of theta is opposite over hypotenuse, and that cosine of theta is adjacent over hypotenuse. You can use any of those that you'd like to find any of the angles that you like. I would, for whatever problem that you're facing, I would just say, okay, what do I have? And then that solves it for you. In this case, we have all three sides, so we can use any one we choose. But most of the time, you're only going to have two sides, and so you'll be forced to pick one. Anyways, for theta 2, I could either use tangent and use 12 as the opposite to this angle here, and 5 as the adjacent. I could also use 5 as the adjacent and 13 as the hypotenuse and use cosine, or 12 and 13 and use sine. Any of those are going to work. But there is one more method I'd really like to go over, which is to recall that for a right triangle, for any triangle, the sides must add up to 180 degrees. But for a right triangle, we know that this angle is already 90 degrees. And so the other two angles have to add up to 90 degrees as well, because 90 plus 90 is 180. So in this case, we already found one of these angles to be 22.62. So for the other angle, we can just do 90 minus 22.62, and this will equal our theta 2. I've already done this, but this gives us 67.38 degrees as our theta 2. Okay, so for problem 5, we're going to create some motion graphs. So I'll let you go ahead and read this information, pause and read that. The first thing we want to do is to sketch a position versus time graph of the runner's workout. So, say time is here on the x-axis, and position, we'll just call our position x on the y-axis. So first, he moves 50 meters in 20 seconds. So I'm going to put a point here at 20 seconds on the time axis, and a point at 50 meters. Point there. Next, he moves another 150 meters, so he's moved a total of, 200 meters in 30 seconds. So we want this to be over the course of 30 seconds. So that would be, 50 seconds over here. 50 seconds and then 150 meters. I think I'm gonna have to make this graph a little bigger. Just try and scrunch this down. Say that down here is our 50. So that was our first point. So here is he moves another 150 meters. So this would be 200 meters. And then 50 seconds, so that's going to be right there. Really going to have to make this really big graph. Next, he moves another 100 meters in 20 seconds, so he's sprinting. So 20 seconds from 50 is going to be 70 seconds, and he moves another 100 meters, so we'll put that here at 300 meters. So that's like right here. And then finally, he moves the last 50 meters in 40 seconds. So 70 plus 40 is, it's going to be over here. It's going to be 110 seconds. And he moves another 50 meters. So that's going to be right here, about. So we have here, and then he picks up the pace a little bit there. And he really picks up the pace for that point. And he really slows down there. This is not the prettiest graph you've ever seen. I didn't really draw it to scale. I'm kind of just hand drawing a graph. And hand drawing graphs takes a lot of practice. But this is what I've got. And this is probably what you'd come up with a traditional hand-drawn graph. You have to kind of graph things using tools online to really do it well. Okay, so for question 2, we want to sketch the velocity versus time graph. So, since it's velocity versus time, we're going to put time on the x-axis and velocity v on the y-axis. Let's see. For velocity, we're also going to have to calculate it. So velocity has units of meters per second. You can see with each of these, we have meters and seconds. So you can reason to yourself that for the velocity for this first part, we're going to do 50 meters divided by 20 seconds. This is going to simplify to say 5 over 2 meters per second. So he's going to move at a speed of 5 meters every 2 seconds, which would be, I think if you divide that, that's 2.5 meters per second. So I'm going to say that this here is 2.5. I'm actually going to put that a little lower. Right here. 2.5, and then this is in units meters per second. And he follows that for 20 seconds. So on the time graph down here, I'm going to say 20 seconds. And since it's a constant speed, it's just a straight line. For the next one, we have 150 meters in 30 seconds. So 150 divided by 30 is going to be 5 meters per second. So it's going to be up here, 5, and he does that for 30 seconds. So over here, we'll put 50 seconds. So you're going to have a disconnect here. So he kind of jumps up to 5 meters per second. And there's a line connecting the two there. Now we have 100 meters in 20 seconds. So 100 divided by 20. This actually also is 5 meters per second. 100 divided by 20 is 5. So we're just going to extend this for another 20 seconds. And then finally, we have 50 meters in 40 seconds. So 50 divided by 40. This is going to simplify to be 5/4. I didn't calculate that ahead of time, but let me do it real quick. Yeah, it is 1.25 meters per second. So that's about right here. And he does that for 40 seconds, so 70 to 40 more seconds is 110. So he drops down all the way to 1.25. He continues it like that. When you have constant velocities, you're going to get these straight lines a lot. It looks a little bit weird, but I promise that this is how it is supposed to look. So now it wants us to calculate the average velocity over the entire 350 meters. Okay, so problem 3 asks us to calculate the runner's average velocity over the entire 350 meters. Velocity is given by, we know that the units are in meters per second, but it could be also the displacement from the start divided by the total time. So in our case, we know that the displacement, assuming that he's traveling in a straight line here, is 350 meters. And the time is going to be how long it took him total. So we have 20 plus 30 plus 20 plus 40 is 110 seconds. And I got all those values from here. So the average velocity is 350 meters divided by 110 seconds, which is roughly 3.18 meters per second. The total distance traveled and the displacement in this case are the exact same. We're going to assume that he's traveling in a straight line. So if you can imagine it, here, let me erase this. Here's the track that he's running along. It's 350 meters long. And he starts at this point over here. And he runs for 350 meters. It takes him differing amounts of time for each little stretch, but his displacement from this point X over here is 350 meters. That is also the same amount of time or distance he traveled. So we know total distance is 350 meters and displacement is 350 meters. So in this case, they're the same. But for this last problem, it says, what if he reversed direction during the last segment and he walked back 50 meters instead of forward? How would the graphs change? Instead of redrawing those graphs, I'm going to show you with our track again. So here's our track. It's still 350 meters. But this time what happens is he runs all the way to this point here, which we'll say this point is 300 meters. And then he turns around and he walks back 50 meters. This segment is still 300 meters. And so the distance is 300 meters plus the 50 meters is 350 meters. However, the displacement is actually only this to this. So we have displacement of 250 meters. This is going to change the position time and velocity time graphs because both position and velocity are vectors, meaning they have direction. He reversed direction, and so at some point it is going to be, for velocity, we would have a negative velocity. So velocity, our graph looks something like this. Instead, it would look like this, having a negative velocity. And for our position, it looked kind of something like this. And instead it would look like this, and then you would have a negative position, and so it would go that way. Okay, so for this next problem, we have a rescue vehicle driving 5 kilometers north in 6 minutes, and then 3 kilometers north in 4 minutes. So it's kind of like it's going north, so it moves this far, 5 kilometers in 6 minutes, and then it moves 3 kilometers, so it's like almost half that. It's more like here. 3 kilometers in 4 minutes. So the first thing we need to do is convert to meters per second. So we have 5 kilometers for 6 minutes. In 5 kilometers, there are 5,000 meters. And then in 6 minutes, there are 360 seconds. And then this simplifies to be, if you do the division, it is 13.9 meters per second. Then for the next part, we have 3 kilometers over 4 minutes. In 3 kilometers, there are 3,000 meters. In 4 minutes, there are 240 seconds. And then if you plug this into the calculator, you get that it goes 12.5 meters per second. So 13.9 is the average velocity for the first segment, and then 12.5 is the average velocity for the second. For this next part, we want to calculate the average velocity for the total trip. So we need the total displacement, which is 5 kilometers plus 3 kilometers. So that is 8 kilometers. And then the total time, which is 6 minutes plus 4 minutes, so that is 10 minutes. Doing our conversion, that is 8,000 meters for 600 seconds. And then this simplifies, if you plug it into the calculator, it is, let's see, 13.3 meters per second north. Next question says, if a vehicle drove 5 kilometers north, then 3 kilometers south, what is the total displacement and average velocity? So let's say we've got 5 kilometers this way, 5, and then 3 kilometers this way, 3. This distance from the starting point is only going to be 2 kilometers. So the displacement is 2 kilometers. Now let's say it still takes the same amount of time, so our 10 minutes. That would be 2 kilometers per 10 minutes. This is 2,000 meters per 600 seconds. And then that simplifies to 3.33 meters per second north. It's important to make sure that you distinguish which direction it is. So in this case, it's north. And let's say that, just for food for thought, if they had instead gone over here, say 7 kilometers, it would be negative 2 kilometers would be the displacement. And then this would be a negative 2 kilometers. And so you would get negative 3.33 meters per second. And so that would actually be south, because in this case, we're considering north to be positive. Okay, next question. We have a jogger running 200 meters east and then 200 meters west in equal times. What is the average speed versus the average velocity? And explain the distance, or the difference. So a couple key things to note. We have the total distance is 400 meters. However, the total displacement is actually 0 meters. Reason for this is, 200 meters east and then 200 meters west. You end up at this exact same starting point. So you haven't actually moved at all. For speed, let's say that they just move with a time t. The speed is distance divided by time. So it would be 400 over t equals your speed, s. Your velocity is your displacement divided by time. But we found that our displacement is 0. So 0 over time equals velocity, so velocity is 0. Again, the difference here is that distance does not have a vector, like it doesn't have a direction. Displacement does. A way that I like to think of it is that I was born in Salt Lake City. And so when I'm in Salt Lake City, if I were at the same hospital that I was born at, my displacement for my entire life would be 0 meters. However, my distance traveled is obviously not that. I've been to Delaware, I've been to all over the United States, I've been to Poland even. So I've traveled a lot further than 0 meters, but my distance from my starting place is 0 meters. And that is my displacement. Okay, now we have some two-dimensional displacement. So we have a search drone. It is deployed to scan an area, and this is how much it travels. Draw the displacement vectors and the resultant displacement vector. So the way that I like to do it is saying that it travels these in order. So first 400 meters north, then east, then south. So first we have 400 meters north, then we have 300 meters east, and then 200 meters south. The resultant displacement vector is the vector that happens between your starting point and your end point. So that would be this here. I'll draw it in a different color. So that is our final displacement vector. So now it wants us to use the Pythagorean theorem and components to calculate the magnitude of the total displacement. So we can draw a line. I'm actually going to get rid of our vector. I'm going to make this a little longer because this should be twice 200. So our vector would be here. So we can draw an imaginary point here where we realize, okay, since this whole distance here is 400, but we know that half of it is 200, this portion right here is 200 meters. And then we know that this portion right here is 300 meters. So Pythagorean theorem, remember, is c equals square root of a squared plus b squared. Plugging in our a and b, our legs, we get c equals the square root of 200 squared plus 300 squared. And if you plug that into the calculator, you get that the magnitude is 361 meters. So that is this here. Now it wants us to use trigonometry to calculate, specifically arctan, to calculate the angle of the resultant displacement relative to north. So if we have north here, and then our displacement vector is this way, what it wants is this angle relative to north. So going away from north. So it wants this theta here. You can see in our diagram that is this theta here. Using arctan, we know that tangent of theta equals opposite over adjacent. So our opposite angle from that theta is, our opposite leg is 300, and our adjacent leg is 200. And then this can just be simplified to 3/2 for the calculation. So then you use tangent inverse of 3/2 equals theta. I've already done the calculations. Theta is, let's see, it's 56.3 degrees east of north. And again, because looking at this part up here, this is north, over here in this direction is east. And so if we're going east of north, we're going towards east, so in that direction. So this angle here is going to be 56.3 degrees. Okay, so now it wants us to write the displacement in the form magnitude plus direction. I'm just going to do this. It makes more sense when you see it. So it has traveled 361 meters at 56.3 degrees east of north. Now suppose that the drone must return directly to its starting point. What displacement is required? So we know that it needs 361 meters because it's 361 meters away. And we instead want it to move at 56.3 degrees west of south. Let me explain that. So let's draw that. So here's south, and then this is the direction it needs to go in. This way is west. Here's west over here. So you can see that this angle is going to be the same as the other one, where this was north, this was east, and this was our theta. But it needs to go in the southwest direction, because over here in this diagram, this point is to the northeast of this point here. So it has to move the opposite direction, southwest. Reflection. Why is the displacement shorter than the total distance traveled? This is kind of, again, just exactly what I was saying. We see our displacement is 361 meters. And drawing that arrow there in red shows, okay, even though it's moved 400 plus 300 plus 200 meters total, it's only moved 361 meters away. Remember my analogy from where I was born.